Hello guys, you're welcome to this lecture on logarithmic functions. So in a couple of videos, I'll do a lecture on logarithm functions as well as exponential functions. And then we'll look at how you integrate these functions. And then also we'll look at some inequalities of log functions later on. But for now, we just want to look at log functions. So I'll give you, basically I'll start with the general, or if you like, common logarithmic functions. And then we'll look at some laws of logarithms. And I'll move on to a special case, the natural logarithm, all right? And then laws of the natural log, and then derivatives of logarithmic functions, and then how you differentiate logarithms. And then we'll end with the natural logarithm as a limit, okay? You can define it as a limit, so we'll end with that. Okay, so here's the basic definition for the logs. You've probably seen this before. The log function with the base a is denoted by this, log to the base a. This is a subscript, such that log to the base a of x is equal to y implies that a raised to the power y is equal to x. On the other hand, if a to the power y is x, you can also say that then the logarithm to the base a of x is equal to y. So you can move from here to there, or from here back here, okay? A has to be positive and not equal to 1, okay, for this definition to hold. So we'll see, as I'll show here, that the log function is the inverse of the exponential function. We'll look at exponential functions later on, but you know something about exponential functions. So for example, the function f of x is equal to a raised to the power x is an exponential function. If you use the cancellation properties, cancellation equations of inverse functions, then you can let f of x be a to the x and the inverse of it be log to the base a of x. And you can actually show that these two functions, the log function as well as the exponential function, are inverses of each other. So if you remember, all you do is find the composition of the inverse and f, that is f inverse of f of x, all right? Now, if they are inverses of each other and you carry out this operation, you should end up with x, okay? And we'll see that that is what we get. So basically here, we're going to start with the inverse function, and wherever we see x, we replace it with a to the power x, right? And so we have log to the base a to the x. And of course, from the definition of the logarithm, this is equal to x, right? In other words, log to the base a of x is equal to y means that if I raise a to the power y, I get the argument of the log, I get x here, right? So if you have this, the number that you raise to a power so that you get a to the x has to be x, right? A to the power x is this guy. So log to the base a to the x has to be x. So we've shown one side of it. The other is to do a composition of f and f inverse so that you have f into f inverse of x. In this case, we start with the function f, and wherever we see x, we replace it with the log, with the inverse, right? So this is a, and then x here will be log to the base a of x. That is why we have it here like that, okay? Now, also from the definition of logarithms, we can easily see that a to the log to the base a of x is x2, and I'm going to show that here. Now you see that if I have log to the base a of x is equal to y, I can raise both sides to the power a, right? They are equal. So a to this power has to be equal to a to this power, right? But a to the power y, we define as to be x, right? So this has to be equal to x. Therefore, this guy here is equal to x. So the main point here is that the log and the exponential functions are inverse functions. They are inverse of each other. Okay, that is the main point of this slide. Okay, and we have shown that here. Now here are a couple of laws, okay, or if you like properties of logarithm functions of logs. if x and y are positive numbers, then the log to the base a of x times y is equal to the sum, right, of the logs. So this is equal to log to the base a of x plus log to the base a of y. Okay, so the product results in a sum. You can go the other way around. It means if you have a sum, you can write it as a product, right? The sum of the logs is equal to the log of the product. Okay, and then log x over y here will be equal to the difference, will be log to the base a of x minus log to the base a of y. And if you have a difference and the bases are the same, you can turn it into a quotient, right? X over y. That's the second one. The third one is log to the base a of x to the power r. Basically, you can take this exponent here and bring it, multiply it by the log. So you can write it as this, where r here is any real number. Okay, so you should know these. These are very important. Okay, I will show proofs of them here, so that later on when we meet the laws for the natural logarithms, we don't need to prove them. We can basically use these ones. Okay, that's why I'm going to show these proofs here. Then we don't repeat it. Okay, so how do we prove the first one? Well, we want to show that log to the base a of x times y is log x plus log y. All right, the bases are the same, so I'll just say log. So you can let m be equal to log x and n be log y. Okay. Now, from the first one, from the definition of the log, this means that x is equal to a to the power m, right? And from here, y is equal to a to the power n from the definition of logarithms. So we know this. So I can multiply them. Note that what we want is we want to multiply and show that, right? We get a sum. If you multiply the two things, you get xy, a to the n times a to the m. But because the bases are the same, you can add the exponent, right? So you have a to the power m plus n. Okay, we'll come to exponential functions, but this you've seen before, probably in high school, right? This indices. Okay, so x times y is a raised to the power m plus n. Good. Now, we can take the log of both sides, right? Here, if you go back here, you have xy to this. Take the log to the base a of this, log to the base a of that. If you do that, you're going to have log to the base a of xy, and then log of a raised to the power m plus n is equal to. Now, here also, we are using the definition of the logarithm, right? That this, you can basically pull this down here, and you have m plus n, right? Log to the base a of a. Okay. And of course, this is just a to the base a of a is just 1. So this basically is m plus n, right? And that you can also tell from the definition. You need something here such that if you raise a to that power, you get what is here. And that has to be m plus n, right? Okay, so we have this. Yeah, again, I've mentioned this from the definition of the logarithms. Log to the base a of a is 1, okay? So we get that log to the base a of xy is equal to m plus n because this is 1. But m is log x and n is log y. So log to the base a xy is equal to this. So if you have a product, it can turn into a sum. Okay. Okay, that's the first one. The second law, log x over y is log x minus log y. We'll do the same thing. We'll let m be log x and n be log y, and then find the quotient, right? Take x over y. X over y will be equal to, well, note this. Here, this from the first one, you know that x is equal to a to the m, right? And y is a raised to the power n. So x over y is actually, we know x is a to the power n, which is this, okay? And y here is a to the power n, so we have that. And this we can rewrite as a to the n minus n, okay? So once you are here, you can take the log of both sides, right? If you do that, log a x over y and log of this guy, we've come across this before, we can pull this down here. I have m minus n multiplied by log to the base a, and this is 1, so I just have m minus n, right? So log of x over y is m minus n, but m is log x and n is log y. So boom. Oh, actually this guy here should be a y. Okay, that's a typo. It should be y, not g. Okay, good. So we have proved the second one. The third one, log to the base a x to the r is r times log to the base a of x. Okay, so here you can let m be equal to log to the base a of x as we've done before. And this, of course, means that x is equal to a to the power m, all right, from the definition of log. Now we can raise both to the power r. So raise this to the power r, this to the power r, and that gives you this. Okay, now you have this and this, you can multiply the exponent here. So that gives you a to the power r times m, right? And then you can take log to the base a of both sides. So you have log to the base a of xr is equal to log of a to the rm. Again, you can bring this down here and log to the base a of a is 1. So you have rm. Okay, so you have a r multiplied by the m. But we know m is log to the base a of x, so that log to the base a of x to the power r is just r times log to the base a of x. Okay, so using this procedure, you can actually show this property here of logarithms or this law. Okay, good. So we've covered the three main laws of logarithms that you should know, right? You use this often in solving problems, simplifying expressions, and even differentiating log functions. So keep that in mind. Now, so what we've shown here, log is general. The a here is any number, right? A here can be any number. But now we want to move to a special case of log functions where a is just not any number, but is the number e. And then we'll talk about why that is important. So the natural log is actually a special case, as I just mentioned, of the general or common log, all right? But now the base is e instead of just a or any number, okay? And the e is approximately equal to this. I'll show it later. So you replace the a there, the number that we'll be using for the base, with e, okay? In the general or common logarithms. And so the natural log is actually log to the base e of x, and log to the base e is ln x, okay? Sometimes called ln x or ln, all right? Here are the first set of properties for the natural log. So ln x is equal to y, of course, implies that. Note that whenever you see the ln, right, and you're confused, you can always replace it with log to the base e, okay? And then it gives you an idea of the definition of it. So ln here is log to the base e. So if ln to the base ex is equal to y, then of course e to the power y is equal to x. That's what we have here, okay? And ln to the base e of x is just x. So it's like ln and e cancel each other out, right? And all you have is x, as if they cancel each other out. Okay, in the same way, if you have e to the ln x, is also x. So again, ln and then e and the ln appears to cancel each other out, right? And then you just have x here. So keep these ones, they come handy, right? When you're solving problems, okay? And note that if we let x be 1 in here, for instance, if x is 1, then I'm just going to have ln e, and it's equal to 1. So it means that ln of e is just 1. So the natural logarithm of e, then the number e itself is just 1. Okay, so take note of this simple expressions here. They become useful later on. Okay, here is another property of the natural logarithms. I'll show you why this is important. So we want to show that log to the base a of x is equal to ln x over ln a. Okay. In other words, if you have the logarithm to any base, you can always convert it to the natural logarithm, right? The right-hand side is all natural logs. And why that is important is that, for instance, if you want to use your calculator to find log to the base whatever, 7, right? Of some number. Often the calculators don't come with those bases, but they come with the natural logarithms. So instead of any base, you can actually convert this into the ln function, right? The ln, and then you compute it. So that is one advantage of this expression here. We can prove it. Let's do that. Let m be equal to log to the base a of x. Then of course it means x is a to the power m. I can take the ln of both sides. So ln x is ln a to the e, ln a to the m. As we saw in the laws, I can bring this m here. So I have m ln a, okay? So I have this. So I can solve for m. So m is just, okay, this and that. M will be ln x all over ln a. So you have this. But m is log x, log to the base x. So log to the base x is equal to ln x over ln a, as expected here. Okay. Once again, it comes handy because you can convert from any base, if you like, right? The log of any base to the natural logarithms. So also note that. Okay. The natural log actually has another definition. You can actually define it using integrals. And this is how it's done. It's defined as this. The natural log of x, or ln x, is equal to the integral from 1 to x of the function 1 over t dt. Okay, this is for all x greater than 0. Okay, so for the natural log, it is defined for x greater than 0. It's not defined for negative values of x. Okay, it's not even defined for when x is 0. When x is 0, it goes to negative infinity. We'll see that later. So keep that in mind. The natural log is for positive values of x. Okay, now if x is 0, then ln x can be interpreted, right? You've seen some kind of integration before, right? Even though we'll do integration, but you can interpret the integral of a function as the area under a graph, right? So for positive x, ln can actually be interpreted as the area right under the graph of 1 over x, as we see here, right? From, let's say, 1 to x. If you have the graph of 1 over x, the integral from 1 to x, the area under this, okay, can be interpreted as the natural logarithm of x, okay? You can do that for values that are less than 1 as well, right? But greater than 0. So that is what I've just plotted here. So from 1 to some x, but x is less than 1, okay? You can do that. And then when you do that, you're going to have an area as well. I'll show that in that case, the ln is actually negative, okay? The area is positive, but it's negative because you have to negate it when you interchange the upper and lower limits of your integration. Okay, so we'll see that later. So keep this in mind. This is another definition for the natural log. It's the integral from 1 to x of the function 1 over t dt. Okay. So as I mentioned, if x is greater than 0, right, is greater than 1, then the ln function is positive. So you can see here, from here, when x is greater than 1, from 1 onwards, you see that the graph is actually positive, in the positive y-axis. Okay, but when x is less than 1, it is in the negative y, so ln becomes negative. So for x less than 1, ln x is negative. And that is because if you go back to the definition, we said ln x is the integral from 1 to x over 1 of 1 over t dt. For x less than 1, you want the lower limit to be smaller than the upper limit. So you have to interchange this. But when you do that, you need a negative. So you have a minus integral x to 1 of 1 over t dt. All right. Now the area itself is positive, but when you negate it, you get a negative value. So when x is less than 1, ln becomes negative. Okay. And as you approach 0, this guy actually goes to negative infinity. That is why x has to be greater than 0 for the ln, the natural logarithm, to be defined. Okay. Okay, good. So keep that in mind too. here are some laws. I'm not going to prove all of this. These are just laws of the natural logarithm. Okay. This is easy to prove from the previous ones. If x and y are positive numbers and r is some rational number, then we can show that all these hold. Ln 1 is 0. The natural log of x times y is ln x plus ln y, right? So basically, you can use the general logarithmic properties or laws that we proved, right? To prove these ones, all you do is that you replace the a that we used with e, and you get the same same laws from b to d. Okay, so ln x is this. When you have a quotient, it becomes a difference, right? If you have a power here, you can bring the power down. You have r ln x. Okay. So for a, you can actually prove it using this definition of the ln. We want to show that ln 1 is 0. So I can put 1 in place of x. So ln 1 here, I integrate from 1 to 1. If you remember from your integration, if you integrate from the same limit, right? From a to a, the integral should be 0. Okay. So ln of 1 is actually 0. You can see that from the graph as well. You see, this is the graph of the ln function. At 1, ln is 0. Okay. So keep that in mind too. Ln is 0 at 1. When it's less than 1, it goes to negative infinity. So the values for x less than 1 are negative, okay? And then when x is greater than 1, the values of 1 are positive, okay? Good. So our next subtopic here is how do you find the derivative of logarithmic functions, given a log function, how do you differentiate it, okay? So we want to look at that. First, we'll prove this, and these proofs will actually tell you how you differentiate log functions, right? The derivative of a to the x, the x is given by a to the x ln a. Actually, this is an exponential function, but it's very helpful in showing or improving that the derivative of the log is given by this. That's why we need this first. So we'll prove this one first, and then we'll use that to do this, okay? Okay, then when we get to exponential functions, we'll just apply this. We don't need to prove it anymore. Okay, so we want to show this, the first one, and then it will help us to do this one. How do you do that? Okay, you can let, oh, this is a typo, so this is x. Oh, no, it's correct, all right? A can be written as e to the ln a. Remember, we said that the e and ln appears to cancel each other, right? So this appears to cancel and just get a, okay? So a can actually be written as this. So which means I can raise both of these expressions to the power x, right? So have a to the x and this guy to the power x, okay? And so now I can differentiate each of these. So d dx of a to the x is the same as the derivative of the exponential. We know how to differentiate the exponential, right? Basically, you leave this and differentiate whatever is up here, all right? And when you differentiate whatever is up here, you just get a ln a. The x goes, right? And you just get ln a. So if you differentiate this with respect to x, all you get is e to ln ax, the same thing, multiplied by the derivative of the exponent, which is just ln a, okay? But as we noted, right, this thing here, this, note that ln a times x, the x can be behind here, right? Which means you can take it up here. So this is the same as e to the ln of a to the power x, right? Multiplied by this ln, okay? So, and again, remember that the e and the ln appears to cancel each other. So this is basically e to the x, which means d dx of a to the power x is actually a raised to the power x. This, if you evaluate this, multiply by ln a, okay? Or if you like, you can go back here, right? You can go back here. We already know that this guy here is a to the x. So you just put it here, right? You actually don't even need this. So d dx of a to the x is equal to a raised to the power x multiplied by ln a. Okay, so if you differentiate this exponential function, this is what you get. And I said we need this because this is it will help us to prove this one. So let's prove this. We have d dx of log to the base a of x is equal to 1 over x ln a. How do you prove that? Well, you can let y or z, in this case y, be equal to this log function. And from the definition of log, this means that a to the power y is equal to x. And then we can try to differentiate both sides with respect to x. So d dx of this, you differentiate x, you get 1, okay? And then we apply the chain rule to this. Note that a here is raised to the power y, but we are differentiating with respect to x. So what we want is to differentiate with respect to y, then it's easy for us to differentiate this because we've already shown this, okay? Let's replace x with y, and this will be y, right? Okay, so you use the chain rule here. d dx will be d dy of this times dy dx, right? Using the chain rule, and it's equal to 1. This is 1. Okay, but this guy here, this guy, we know how to do it. This is the first property. We know how to differentiate this. If you go here, we know how to differentiate those types. Once again, if you replace the x with y, d dy of a to the power y will be a to the power y ln a. Okay, so you can plug that in here. Okay, and then you're going to get a to the power y ln y dy dx is equal to 1, right? Good. Now, we know that a to the y is x from here, right? A to the power y is x. So this guy is just x ln a dy dx is equal to 1, all right? We want to find dy dx, okay? So we divide through by this. So dy dx is equal to, of course, dy dx means d dx of the log is equal to 1 all over this guy, x ln a, and we have proved it. So if you're finding the derivative of the log function is basically 1 over the variable in here, x, times ln of the base, which is this. Okay, good. Good. So that is basically on how to differentiate logarithmic functions. Once again, to convert this to one with the natural log, all you do is replace the a with e. All right. We know this. We know d dx is equal to this. This is what we just proved, right? So if I replace the a with e, I'm going to get d dx of ln x, right? Once log to the base e is x. I mean, log to the base e is ln, right? So that gives me ln x, and ln e, we said is 1, right? Ln e is log to the base e of e. So that is also 1. And so all you have is 1 over x. So that is why the derivative of the ln function just gives you 1 over x. Okay. We'll look at a more general form of this later on. But you've already probably come across this before. So the derivative of the ln x is just 1 over x. Okay, good. Let's look at these examples. This says that expand the following expressions using the laws of logarithms. So we just want to, if you like, expand these guys using the laws that we just learned. This one, of course, is a quotient, right? Is this over that? So we can convert into a difference. So this will be ln of the numerator minus ln of the denominator, right? So that is it. Okay. Well, if you want, you can also split this, but it's not necessary. This would be ln 2 plus ln 3 minus this. Okay. This one will be similarly, this will be ln of this minus ln of the denominator, right? Now, this product, we can write it as a sum, right? We can write this as ln of x to the power 1 over 3 plus, because they are multiplying, plus ln of y to the power 2/3 minus ln of z to the power 1/2. Well, from some of the laws of log, right? You can bring this down here. So you have 1/3 ln x plus, you can also break this down here. That gives you 2/3 ln y minus bring this, that gives you 1 over 2 ln z. And so that is expansion of this. Okay. So basically that is that. On the other hand, instead of expanding, you can actually use logs to write expressions as a single expression, right? You can go the other way around. So if you have ln 4 plus ln 6 minus ln 12, how do you write it as a single expression? Same for this. So if you have this, well, ln 4 plus ln 6 minus ln 12 will just be equal to, because this is a sum, you multiply them, right? This will be ln of 4 times 6 minus ln 12. Of course, 4 times 6 is 24. So this is just ln of 24 divided by 12 because this is minus, right? This goes into here too. So this is just ln 2. So we have written this as a single expression. When we come to this one, we have 3 ln 2 minus 1 over 2 ln of x plus 1 should be equal to, we can take the 3 up here. So we have ln 2 raised to the power 3, right? From the laws. So I get this. The same way I can take this half up here. And I have ln of x plus 1 raised to the power 1 over 2. Okay, it's subtracting, of course, 2 to the power 3 is 8, right? And this is the square root of this guy. So the minus means that I have to take this all over this guy. So I'm going to have ln of 8 all over the square root of x plus 1. Okay, good. So that is that. Here is, so we are done with this. Here is a theorem. Yeah, this is the general form that I talked about. Okay, that if u is some function of x, then ddx of ln x is 1 over x. We've already shown this already for x not equal to 0. This is a more general case. ddx of ln u, where this u here is a function of x, is equal to 1 over u du dx. Plus u is not equal to 0. Otherwise, this is undefined. Okay. So this is important. In other words, if you are finding the derivative of the log or ln here, all you do is that take 1 over the argument of the ln, right? 1 over the ln, and then times the derivative of the argument. Okay, you use this a lot, all right, when you're finding derivatives of log or ln functions. Okay, so this is actually very similar to this. This is ddx of ln of some function. What it means is that take 1 over that function, so 1 over g of x, and multiply by the derivative of what is here. So you get g prime of x all over g of gx. All right, so one we have already discussed. This one you can try to prove it. I mean, from what we've done already, you could use the chain rule to actually prove this, okay? So you can try it. Good. Here are some more examples. You want to find the derivatives of the following functions. F of x is ln of 2x plus 3, and g of x is ln x all over x plus 1. And then y is ln the absolute value of cosine of x. Okay, how do you find the derivative of that? You can use these guys here, right? Or if you like this, okay? So for this, you have to divide by all of this and then multiply by the derivative of what is in there. So this f prime of that will just be 1 over 2x plus 3. Then you have d dx of all of it. So find the derivative of this. Derivative of this is just 2, right? This is a constant, so it's 0. So you're just going to have 2 times that, which is 2 over 2x plus 3. Okay. Then this guy is a quotient, so you can use the quotient rule, right? So g prime here is equal to, I leave this, right? Then I differentiate ln x, but the derivative of ln x is 1 over x. We've seen that already. All right, minus, then I leave ln x and I differentiate this and just have, this is just 1 if you differentiate x plus 1. So you have this all over the square of that, right? The quotient rule. And then the rest is algebra, just simplify it, okay? This is the same as x plus 1 over x minus ln x over the squared. This is equal to, you can multiply the top by x and the bottom by x so that this x cancels. We have x plus 1 minus x ln x because I'm multiplying through by x here. And I multiply by x, I get this. So this is equal to that, okay? Good. Then we need to differentiate C, right? Y is equal to this, okay? Because it's ln of this, once again, you have to take 1 over all of this and then multiply by the derivative of cosine, right? So this is 1 over cos x multiplied by the derivative of cosine, that is minus sine x. So this is just negative sine x over cos x, which is negative tan of x. All right, good. So these are just examples from the properties that we've looked at. Okay, I want to end the video here. Then when I come back, I will look at logarithmic differentiation and then the natural logarithm as a limit. Okay, I don't want the videos to be too long, so I'll try and end here, and then I'll come back and then I'll continue from this place. Okay.